Hello and welcome to this new video where we discuss mathematics and physics on the board. In this video we are going to combine a few of the videos we've done before, one on the divergence theorem and the other one on the hydrostatic law or equation for the pressure in a fluid. Okay, so that's what we are going to use today in order to discuss the concept of buoyancy. Right, so let's set the stage. So buoyancy, we kind of know what it is qualitatively, right? So if you immerse a particular object in a fluid, and this fluid, there are some conditions that this fluid must kind of have or satisfy. One of them being that the fluid must be kind of static for the most part. Of course, if there are winds and currents everywhere, then the things are going to be quite different. But anyway, so you've got buoyancy is if you put an object in a fluid, then in principle is going to be subject to a force that opposes its weight, and in fact the magnitude of that force is actually the um, the weight of the displaced part of fluid to actually put in the to immerse the object in it. Okay, so that's kind of the buoyancy law. In Europe, at least in France, we call this Archimedes law. So probably it was described by Archimedes in some shape or form. But the bottom line is that it's a very old empirical law. And what we want to show here is that basically it has a sort of, if we look at the mathematics, there's a sort of obscure connection to the divergence theorem. And that in some way, at least that's one way to understand how this works. So let's see how that goes. So here we consider an object of completely arbitrary shape. And so that's what I've tried to do. It looks like a bit like a puzzle piece, but so that's kind of what we have. You need to imagine this object in 3D, by the way. So that's a three-dimensional object, and the domain that is occupied by particular object. So the object here is made of some material, usually solid, and that's it. Okay, so inside there is no fluid. Okay, so you can put some hash here to make sure that this is not the same as a fluid surrounding it. Okay, at least that's one way to view it. So I named that domain omega. The boundary, the surface, the enclosed surface covering it is d omega. That's a traditional notation I've used in many videos now. And basically that's it. Now, the density of the fluid, I'm going to call that rho f, okay? Because there could be, there is obviously a mass density as well for the object embedded or inside the fluid. And then we assume the fluid to be in hydrostatic equilibrium. So nothing is moving, the fluid at least is not. And of course, there is always the problem of if this object moves, then fluid has to be moved around as well, but we neglect that problem at that stage. And then we imagine that there is a pressure field that is, as usual, pressure that in principle depends on the location, but here we say that it only depends on the height, okay? That's because we are under gravitational consideration. So maybe I need to put that somewhere. So that's so effect of weight, okay? That's related to the hydrostatic equilibrium anyway. And the question we want to ask is basically what is the total force that is due to the pressure on the fluid? Now, in principle, that looks like a very, very difficult problem. And in fact, let me write down what this problem in principle should look like. So the total force, I can put an actual vector here, is going to be something quite complicated. So that's going to be the integral. I put here a circle to say that it's over the total enclosed area that is bordering the solid phase or whatever is immersed in there. So that's the over d omega. And then of the pressure, so let's say imagine for now that I'm at different locations on the surface. Then this is, I need to put here n of r. So here this is, just to represent this n of r is a normal vector at r. And usually this is a normal outward vector. So let's say here this is the location of r1, and here you may have n of r2. So if this point is called r2, and here this point is called r1. Okay, so that's basically what these vectors n are. And then ds. So basically I'm integrating over the surface of that stuff, then the pressure and minus, okay, because the pressure acts from within and the vectors here are outward going, so essentially I want a minus there as well, okay. So once we have that, then what do? What I can check, and I will do it on the other side here, is I can try to find, because that's the only thing I'm interested in, so I want to know the projection of F on the z-axis. And the way I know that, this is simply F dot z, so that's a unit vector going in that direction, and that's going to be equal to the integral, and then here over d omega, and then I've got P r, and then n of r dot z ds. But I have actually another way of writing this down. I can write this as being equal to d omega, and then I can create a fictitious vector that doesn't exist, but a vector field that is p of r in the z direction, and then dot product ds, and where ds is equal to n of r ds. So that's a traditional element. But the reason why this is different is because now I've actually written a flux. Okay, so before it was like some weird looking thing, and now here this has the structure of a flux. And it's not any flux, it's actually a flux across a closed surface, where I need to imagine, by the way, where if the solid were not there, the fluid would be kind of all fine and behaving normally and all that. Okay, so I need to obviously imagine that everything is fine. So if that's the case, then, by the way, I forgot the minus again, so that's minus here. And then what that means is that I can use the divergence theorem. And what the divergence theorem tells me is that this is minus the integral over the entirety of the domain here, and then of the divergence of P of R Z, and then dV. So that's here the volume element. So I'm integrating now over the entirety of the volume the divergence of this fictitious pressure kind of vector field. Okay? And the thing is that here, again, what I need to imagine is that it's as if I had removed that particular solid object, and then I'm looking at how the fluid is going to behave and how the pressure field is going to behave of the fluid within that stuff. Okay, so that's kind of what we are imagining. It's as if we had removed the solid part here. Now, once we have done that, I need to find out what is the divergence of that. Now the divergence of a field, of any field, A, is going to be equal to dAx dx plus dAy dy plus dAz dz. But as it turns out here, I've only got a z component. So actually, this stuff is equal to simply dp over dz. Okay? And that's where now I'm using my knowledge of hydrostatics, because we had found that dp over dz in the previous video. I'm going to put, I think it's going to be there, I'm going to put a link to this video. We had found that dp over dz was equal to minus rho f times g. Okay, so here this comes from hydrostatics. Under the action of weight. Okay, so once we're there, we just need to, there is a minus times a minus, so I'm substituting basically dp over dz by minus rho f g, and so I've got minus minus, so that's plus. Then I can put the g outside because g is the acceleration constant of the weight on Earth. Then I've got omega here, and then I've got rho f, and then dv. And so what I get in the end is basically it's equal to plus mf times g. So all in all, we've got that, and I'm going to call that fb for buoyancy. That's equal to the actual weight of the displaced fluid in the opposite direction to the actual weight. Okay, so that's the actual result, and that, you see, that's coming from the divergence theorem. So that's the so any immersed object is subject to a force, an opposing force, in fact I should say a force opposing their weight, which is of magnitude equal to the displaced mass, equal to the weight of the displaced mass. There's most no ink anymore in that pen. Okay, so that's a buoyancy law, and then this can be used in any kind of setting you want. If you've got partially immersed stuff, that's again going to be equal to what is partially being immersed, etc., etc. But you see, the beauty of it is that it comes from that. There is some conceptual aspects to it that are not necessarily trivial. Okay, the fact that you actually evaluate the force on that contour, and then imagine as if there was no solid thing, and then you carry out the calculation because the gradient field of the pressure exists when this particular solid object is not solid, or whatever object is not there, is a conceptual aspect that, you know, that maybe warrants further discussion from a conceptual standpoint, but at least from a mathematical one, that's fairly clear and quite beautiful short result to be put forward. Okay, so that's it for today. If you've got any questions or comments, by all means, do let me know in the comment section, and otherwise, see you in the next video.